Hi, I'm Ray Huhnke. I'm Director of our Bio-Based Products and Energy Center at Oklahoma State University, as well as Professor in Biosystems and Agricultural Engineering. It's my pleasure to serve as the panel moderator today, but I really need to give the credit for today's gathering of presentations to Tom Richard. He's the one that did all the legwork, and I get the benefit of taking some of the limelight, if you will, from that. So, Tom, I appreciate you pulling this together. In addition, we had a panelist who could not make the trip, so Tom has freely given his time and energy to be one of the panelists today as well. So again, I appreciate his work in this endeavor. If you attended yesterday's general session, the keynote address by Margaret Ziegler from Global Harvest Initiative, her topic was Building New Breadbaskets, the Challenge and Promise of 2050. To me, there were some very sobering estimates or forecasts for the future that included moving from 7.2 billion to 9.6 billion people in the world. 70% of the current fresh water is being used. That needs to or will be moving to 89% of our fresh water supply. There is not any additional land available, so what is available is going to have to be utilized to the best it can for productivity bases, but at the same time we need to look at sustainability. And when we talk about climate variability, that's another factor that we all have to deal with on a short-term as well as long-term basis. Today's panelists, we're going to approach the energy environment nexus as part of that food, energy, water nexus. We're also going to look at policy. I'm going to provide introductions to all of the panelists to begin with. They'll present approximately 15 to 20 minutes, and then we'll have a 5-minute Q&A for that particular panelist. Then we'll have the next panelist until we're all done, and then we'll have a general Q&A following. Our first panelist, Dr. Robert Annex, is Professor of Biological Systems Engineering at the University of Wisconsin-Madison. He received his PhD in Environmental Engineering from University of California, Davis in 1995, after which he held faculty positions at Iowa State University and the University of Oklahoma. Prior to joining academia, Dr. Annex was Senior Engineer at Systems Control Technology Incorporated in California from 1983 to 1991. He is a member of the editorial board of the International Journal of Life Cycle Assessment and is associate editor for the Journal of Industrial Ecology. His research focuses primarily on systems analysis and optimization of biological systems. Next, we will have Dr. Jennifer Dunn. She has an MS and PhD in chemical engineering from the University of Michigan. She is a principal environmental analyst and lead of the Biofuel analyst team at Argonne National Laboratory. In her research, she investigates life cycle energy consumption, environmental impacts of advanced transportation and fuel technologies, including biofuels and battery-powered electric drive vehicles. Her biofuel-related publications focuses on life cycle greenhouse gas emissions of corn and cellulosic ethanol, and life cycle assessment of renewable hydrocarbon fuels and bioproducts, and land use change greenhouse gas emissions. And our third panelist, Dr. Tom Richard, is Professor of Agricultural and Biological Engineering at Penn State University, where he serves as a director of the Penn State's Institutes of Energy and the Environment. He received a BS from the University of California, Berkeley, and an MS and PhD from Cornell University. Dr. Richard's research is currently funded by the National Science Foundation, the U.S. Environmental Protection Agency, the U.S. Department of Agriculture, and the U.S. Department of Energy, where he serves as Deputy Technical Director for DOE's National Risk Assessment Partnership for Carbon Sequestration. He is active member of American Society of Agriculture and Biological Engineers and is fellow and past president of the Institute of Biological Engineering. So first, we'll have Robert.
Ray, thank you very much, and thank you all for coming and listening to me talk. So, bioenergy and water nexus. So, bioenergy and water are inextricably coupled. If we're going to make bioenergy, we're dependent on biomass production, and of course, the vast majority of water that's needed to make a liter of biofuel or bioenergy is used in the feedstock production. And water is already limiting in many agricultural systems. And as we have already heard, agriculture currently accounts for about 70% of the freshwater extractions in the world, and that's only going to grow. So the questions that I'm interested in are, how are the production and use of biofuels likely to influence the future state of water resources, and how can we mitigate the negative impacts and guide development towards sustainable use of water resources and bioenergy? So what you're looking at is kind of a busy diagram, but what it's showing is a water stress index. So it's an index, goes from 0 to 1, and it's calibrated so that the sum of the demands over the available water resources is calibrated to 0.5. So 40% of the unmet demands. And what you see is that there are parts of the world that are already under a lot of water stress. There are also parts of the world where there's a large fraction of the population and where population growth is expected. And this is on a watershed basis, right? So it's not, these are the mega cities. These are watersheds where we're producing biomass, food and feed and fuel. And of course, among other trends, population growth and the related increase in demands on agriculture and forestry to provide that food, fuel, fiber, and energy, right? Food, fodder, fiber, and fuel, are those the 4 Fs that we like to use? Well, and that'll increase more stress on water resources. And in fact, a study that was actually released in 2005 predicts that in 20 years, the world's water thirst for water will grow by about 50%. And the most recent global environmental outlook estimates that by 2025, 2/3 of the global population will live in areas experiencing water stress. And by 2030, the withdrawals are expected to exceed natural renewal by about 60%. And if you look at that map, you can also imagine, if you've seen those forecasts, that climate change is only going to make that worse, right? That where we expect to see more variability, more frequent droughts and more severe droughts, as well as higher amounts of rain, are in the more equatorial regions. So, of course, in some places, there's plenty of water, right? And of course, in some places, much less. So we've had a rather prolonged drought in the western United States, and in certain parts of that region, agricultural production is already fairly severely limited. And so when we export ethanol from Iowa to California, we're doing a good thing, right? We're taking some place where there's a lot of water available for agricultural production, and we're essentially shipping it to California in the form of that ethanol. So there are researchers like Tony Allen that refer to that as virtual water. And I think it behooves us to think about how other people, perhaps not agriculturalists, think about water resources and water use. So there's this idea of shipping virtual water. And of course, any country or region imports water as well as exports water, right? But if we look at the net, so this is a nice picture from ETH Zurich. All of these, I have the little reference at the bottom, and you can find the references at the end of my talk. If we look at the net virtual water flows globally, we see that North America, South America, and Oceania are pretty big water exporters, And Europe, Africa, and Asia are pretty big virtual water importers. And to a certain degree, as you'd expect, this can ameliorate water shortages. So there's a study of the Nile Basin that shows that between 1998 and 2004, 14,000 million cubic meters were exported annually from the Nile Basin, and 41,000 million cubic meters were imported. So there's a net there of 27,000 million cubic meters of water imported into the Nile Basin, which goes a long way towards ameliorating the water shortage. That's about a third of the flow of the Nile River. And so Egypt and Sudan, for instance, were significantly benefited by that. So that sort of makes it clear that not all places are created equal and not all water is created equal, right? So in the Nile Basin, almost all of the water used for agricultural is what we would call blue water. It's water that's extracted in irrigation as opposed to rain-fed. So we need to think about that. So there are these colors of water, and here are the definitions that what people refer to as green water is precipitation consumed directly through by a crop through evapotranspiration. And blue water is irrigation water that's directly used in the crop or in the processing of the downstream products. And then gray water is estimated as the amount of fresh water required in the receiving water bodies to assimilate the waste from that production and meet water quality standards. So we can sort of look at this in world water flows in terms of colors. Now, to a country that's importing some biofuel or some agricultural product, they don't really care what the color of the water is. But globally, there can be some real impacts. So this kind of busy slide shows you some virtual water that's carried in food. So here are the flows to the 5 major wheat importing countries between 2000 and 2004. And you can see that it's broken up. Those circles show you what was blue water and what was green water. So you can see for North America that there was a large amount of green water, and I can't really work out what that statistic is, but you can see that it's something like 40% of wheat production is based on green water in North America. So if we look at these countries, Egypt is the largest wheat importing country, and it imports about 45% of its wheat from the United States. And that's one of those arrows that you can barely see. But Egypt has pretty big imports from several different regions. And wheat grown in Egypt is entirely blue water. It takes about 930 cubic meters per ton. Whereas in the United States, we're actually less efficient in terms of wheat production and the water used. So we use about 1,707 cubic meters per ton, of which about 40% is blue water. So by importing wheat from the US, Egypt saves 930 cubic meters per ton, but the US loses 1,707. So on a global basis, that's 707 gallons of water that is sort of lost to the world. But if we look at it just in terms of blue water, by doing that, we're saving 251 cubic meters of blue water, right? Which is the water we pay for, that we pump, and that is in many ways a more valuable resource. And Egypt recognizes this, and Egypt and other countries have formulated policy. They say we're going to intentionally favor the import of low-value, high-water use crops in order to basically maximize our import of virtual blue water, or save ourselves blue water. So let's move from wheat, which of course is a bioenergy crop, but let's move to that to a little bit of what we know about bioenergy. And I'm not sure how well you can see this, but it's not too bad if you can't, because this is a survey of the literature that sort of says, all right, let's go look at per liter of biofuel made, how much water is needed, both blue and green, by feedstock. And what you see is, well, gosh, it's awfully confusing. There's a few winners and losers. So these are actually ranges. And so it's not surprising that a crop needs a certain amount of water. And if you're in a place where it's all blue water, you're at the far end of the screen, the blue line. And if you're using all green water, you might be at the left end. It's going to depend on what the vapor pressure deficit is, right? How dry you are, how arid it is. We can see a few things. There are some crops like jatropha, which is the second from the bottom, that has big bars under any circumstances. And despite the fact that we've been told it's a miracle crop that'll grow anywhere, not so much in terms of water. We can also sort of see that grasses use a lot of water, and if you're going to irrigate them, that's a problem. If it's green water, it's okay. Corn is actually, even though I give lots of talks talking about corn and the bad things about corn, even having spent years in Iowa, it's pretty frugal in terms of its use of water, in terms of megajoules of bioenergy that comes out the back end. But other than that, we can't really tell too much from this. So maybe what we need to do is go back to first principles just a little bit. And that is not too surprising. If you want to produce a bunch of biomass, you have to transpire a bunch of water, right? The mesophyll cells have to be saturated. If the water is going to evaporate out for the CO2 to come in, a C4 crop, you can see the C4s use less than C3s because, well, right, they fix the CO2 into the bundle sheath cells and they can close down the stomata. In any case, C4s are going to be more efficient. The dotted lines show you a drier climate, right? A higher vapor pressure deficit. So drier places are going to use more water. C4s are going to be better than C3s. But at the end of the day, and of course there's also issues of how much evaporation you get from the soil surface and how much moisture holding capacity your soil has, et cetera. But if you're going to produce more biomass, you're going to transpire more water. And that dotted line there, this is from a paper by Tom Sinclair, and I apologize I didn't put the source on it. He was looking at 9 tons per hectare, metric tons per hectare, and saying, well, how much water do we need? And so I happen to know, having spent years in Iowa looking at corn, that if you're going to have about 9, if you draw that line up and say, well, okay, we're going to need about 250 millimeters of transpirable water. And the available water that rain-fed agriculture in Iowa is right around 300. So I used to have arguments with my friends from some of the seed companies who said we're going to have 300 bushels on every acre because by my accounting, there's just not enough water to get there. We may be able to do everything else, but in any case, so this translates into bioenergy in a variety of sort of interesting ways. So here's the bioenergy water use efficiency across the bottom, megajoules per cubic meter of water, and the primary production up the left side, so megagrams per hectare per year. And based on that previous chart, we sort of see what we would expect, that the trees are that blue line across the bottom, excluding that one green triangle, which is eucalyptus. Eucalyptus is a weed. It behaves like grass. But if we exclude that, you get that line across the bottom. So some trees have high water use efficiency, but fairly low primary production. Grasses, C4 grasses are sort of the winners. So you can get some pretty high bioenergy water use efficiency, right? So per liter of bioenergy that comes out and high productivity. But of course, that's not going to work everywhere, right? I mean, these crops, it's great for somebody like me to throw a chart up like this, but climate matters, what your infrastructure is, what your socioeconomic system is, right? So you're not gonna have one solution in one place, obviously, as we all know. So the climatic, the social, and the market considerations are gonna influence what the composition and the multifunctionality is of the feedstock. So there's different solutions in different places. But at the end of the day, if you think back over what I've said, they all need to be water efficient. I mean, that's what we really know. We're going to try to produce a lot more. We're going to ask a lot more of agriculture and forestry, if those aren't the same thing. And we will need a lot more biomass to meet our bioenergy needs. And ultimately, that's going to require a lot more water. And we have a lot more water demands coming from every other sort of demand. So what does this mean? This means work for us, right? This means opportunities. So a whole range of what people have been working on for some time, but some really interesting new opportunities. Precision agriculture with regard to water use, mobile soil sensors that can move around the field. Of course, remote sensing. I see drones everywhere now. And in Iowa and Wisconsin, there's a number of places that are not typically, you don't think about irrigation, but there's a lot of precision irrigation starting to go on. So crop soil modeling, you see some interesting sensors that Deere is selling field scale solutions to help people do irrigation scheduling and just know how to manage their crop better to use water. on-demand pressurization can actually give you vast improvements in irrigation efficiency. Some of my friends in California are doing that work. Of course, data integration and analysis overall. I'm almost done, Ray. Wastewater recovery. There's lots of opportunities to reuse water, improve soil management. Obviously, a lot of this depends on what is the soil's moisture holding capacity, how are we managing the crop system. Cover crops and winter cover crops can give us biofuel feedstock, and they can also give us less evaporation from the soil, greater soil organic matter and moisture holding capacity. And all these things are engineering solutions, right? Things that we do. And in some places, controlled drainage works, so where we have highly drained soils, corn country, right, where I've spent a lot of my career. We can actually control the drainage so we can make the field dry when we need to get into it, but then we can retain water for the crop and not also, it has big environmental benefits. And you see a picture there of some mixed bioenergy buffer strips and filter strips. So there's lots of opportunities, and I guess I would just conclude that there's absolutely a coupling between biofuel, bioenergy, and our increased demand for limited water resources. And our choices of both the crops and the production will have local solutions, right? What works in one place isn't going to work in another, and we're going to have to design every one of those individually with study, figure out the right equipment, the right management practices, and the development of sustainable water resources is absolutely critical, and it's an opportunity for engineers. So we have to develop ways to reduce the water use in agriculture in general, but in bioenergy production in order to meet the demands of the growing population and climate change and the demands for food, fodder, fiber, and fuel. Thanks very much.
We'll take 5 minutes for questions and answers for Rob at this time. Jim's got one right there. Or Shahab.
Yeah. Thank you. Is there a way of separating the residue, like corn stover and wheat straw and so forth, from grasses in terms of water usage, or having a discussion around those, the difference between the two in a clear way, so, residue versus grasses that you grow, like switchgrass and others that you would grow specifically for energy crop in terms of water usage?
Right, great question. So I'm going to interpret the question is there a way to separate things like residue, corn stover, from energy crops in terms of water use? And I'm assuming it's in terms of water use, right? So this is the classic people who do life cycle assessment, and I'm one of those, is we have to take something, right? So it's a multifunctional system. We grow a corn plant. It produces both of those things as well as some other services, and we have to somehow divide them. And there is no, absolutely rational, objective way to do it. You're going to somehow take the amount of water that was needed to grow that crop, all of its above ground biomass, and divide it amongst those pieces somehow. And there's various rational, semi-rational ways to do it, right? If you're talking about energy, you can break it up by energy content and say, okay, right, this much water is proportional, or the water use is proportional to the energy in the components. And I think that's the most rational way to do it. But, it's a little bit of a fiction in any case.
Thank you for the presentation. I'm intrigued by your discussion of the water theoretical limits of conversion on photosynthesis or producing biofuels. And in C3 and C4 crops, establishing potentially a theoretical upper limit on yield. And how real do you think that is? And do you think that the molecular biologists can break that by 5%, 10%, whatever?
Well, so the first part of that question, how real do I think it is? I think it's actually pretty real. I mean, I don't think I'd stand up here and say it if I didn't. I mean, it's very mechanical, right? For CO2 to move through the spongy mesophyll cell wall, you have to have saturation there. That, you know, you got 99% moisture at the stoma, and if the thing's open so CO2 can diffuse in, water can diffuse out, and it's very mechanical, right? It has very little to do with the physiology of the plant. So there's not that much you can do about that, right? I mean, C4 already does about as good as you can do in terms of moving the carbon to the spongy mesophyll, so when it's really dry, you can shut that down and reduce water loss. And so it's not a simple matter of, well, we're going to change out an enzyme, right? Now, we've done some wonderful things, right? I mean, corn plants now have incredible root structures that, you know, in Iowa, they chase the water down. They capture their ability to pull the water out of the soil and, you know, maintain above that wilting point is pretty incredible. But at the end of the day, yeah, I think that there's not much we can do about water out per carbon fixed in.
Kind of a follow-up on that. I was intrigued with your anomaly of the eucalyptus, and I'm just thought, is the environment, a growing condition, a factor in how you would look at data? I'm from Hawaii, the tropics, and you know, we can grow eucalyptus pretty well, popular maybe not so well. So, you know, and we see some consistency with the temperate crops, or growing the same crop growing temperate conditions, but then anomalies when it grows in the subtropics and subtropics. I'm just wondering, from your experience, is that a fact? The growing conditions, or all year growing conditions, will that kind of put these kinds of crops in a different category?
You know, I don't really know. That piece of data is there and it's taken from the literature, I don't really know the physiology of all the different eucalypts in different, and I wouldn't know. I was sitting here thinking, right, can I even begin to guess? And I wouldn't dare.
I think I'll cut it off now. Rob, thank you very much. Let's give him another hand. Jennifer?
Great, thank you. So I'm going to change gears a little bit and talk about soil carbon, which we've heard a fair amount about this morning in Jonathan's talk, also in the video and from our other speakers. Can you go to the next? Oh, I have the control, of course. So when we think about converting land to bioenergy, we sort of have two options, or maybe three. The first option is that land was already producing the particular feedstock we're interested in. Second option is that land was in some initial state, be it grassland, forest, producing a different type of crop, and now we undergo land use change to produce this new biofuel feedstock. On the other hand, we could have what I'm calling land management change, as well as some other people, where you have something like a cornfield where stover's not been removed. Now you start removing stover, and this land doesn't go a land use change, and that doesn't change land cover, but it really undergoes a land management change. There's some shift in the management process. Either way, land use change, land management change is going to be a shift in soil carbon. And there are a number of factors that influence how that shift will go, which direction it will take, and its magnitude. And I realize I'm speaking to an audience of ag and bioengineers here, so you may be more familiar with these factors than I am myself. But one of the most important factors is, of course, land use history. What was that land doing before? Had it been cycling in and out of cropland and pasture land for decades, or had it been a native prairie? That land use history is very important, as well as the expected yield of the bioenergy crop, both initially after conversion and into the future. The yield could potentially increase over time given advancements in technology and other factors. The climate is, of course, an important driver of what will happen, including levels of precipitation, getting to Rob's talk about water availability. The water and carbon cycles, of course, influence each other. It matters what soil depth you're looking at, shallow depths versus deeper depths, as well as management practices. What's the extent of tillage? What's the extent of residue removal? And so on and so forth. At Argonne, we've really tried to look at soil organic carbon changes upon these land transitions that are important in a bioenergy context from two angles. One is we've tried to understand what the literature is telling us about these soil organic carbon changes, and the other is to use a modeling approach. So if I start by going through what the literature tells us, recently we undertook a meta-analysis of over 100 studies talking about empirical studies looking at these soil organic carbon changes upon land transitions. This figure is one example of the output from that work. We're looking here at changes in soil carbon sequestration rates for several land transitions going from cropland, grassland, or forest to producing corn or miscanthus. And if you have a positive sequestration rate, of course, that means soil carbon is increasing. Negative means you're emitting carbon to the air. That carbon is oxidized, CO2. And then if you look at biofuel production from a life cycle context, that CO2 emissions would count against the biofuel itself. On the figures, you see 3 different sets of results for each land transition. The orange boxes are changes in soil carbon in the shallow depths, the 0 to 30 centimeters. Blue, the changes from 0 to 100 centimeters, and green, the changes from 30 to 100 centimeters. And a couple things to point out about this figure. The first is the large variability, and this is really to be expected. We pulled studies from really around the world, from climates that were relevant to the U.S. Situation, but the bulk of the studies were really from the U.S. itself. But nonetheless, there are differences in how the studies are carried out, site-specific variations that contribute to the overall variability of the results. Secondly, if you can convert cropland to either miscanthus or corn or the other feedstocks that we looked at, like switchgrass, for example, you see, in general, soil carbon sequestration rate there is positive. So you're, on general and average, looking at an increase in soil carbon from converting cropland to these feedstocks. This is just a generic sort of cropland history. On the other hand, looking at corn, if you convert grassland or forest to corn production, the SOC sequestration rate is negative. So there's going to be some carbon emissions there, and that's perhaps unsurprising. If you look at the forest to corn transition, that blue bar for the deeper soil depths, it's the most negative rate that we observed. On the other hand, if you look at converting grassland to miscanthus, you see the SOC sequestration rate, on average, is about 0. So you're really seeing no profound soil organic carbon change there on average as a generalization. But of course, as Jonathan pointed out, and as we see in our own research, there's a lot of spatial variation in what that rate will be, depending on site-specific characteristics. Another question we wanted to get at with this analysis is, well, how long does it take for soil carbon to return to equilibrium after that land transition? And looking at the different transitions you see listed on this slide, we found that for most transitions, equilibrium is achieved after about 20 to 30 years. The exception was converting forest to corn, and that took more like 50 years. This figure, for me, has an important implication for life cycle analysis of biofuels. Typically, we adopt a time horizon in those types of analyses. They may be over a 30-year time horizon, for example, is what EPA uses and what we tend to use in our own work. There's a challenge here in that if an analyst were to adopt an SOC sequestration rate from a year soon after the transition, that annual rate of change, if applied every year over a 20 or 30-year time horizon of a life cycle analysis, that would result in either overestimating sequestration or emissions. So it's very important to adopt a sequestration rate, an annual sequestration rate that's appropriate for the time horizon of a life cycle analysis. And this is a key point that we tried to make in our paper. So this has been discussing our look at empirical studies. There are some limitations that empirical studies pose, some of which are just there are differences in the approach to collecting the empirical data. There are differences in site-specific characteristics, and so it's very hard to make generalizations, or if you're trying to look at one specific area, to pull a number from an empirical study and use it in your analysis. For this reason, and to have a consistent and systematic picture of soil carbon changes upon land use change for bioenergy production, we've used modeling as an approach to get this type of results that we need. Using modeling allows you to capture site or region-specific aspects of a system that you're looking at. You can look at different ag practices like tillage rates, stover removal rates, and you can really control these variables systematically, help you understand trends, drivers, with spatially specific focus. And we can also incorporate different time horizons. So we use a sub-model of the century model in our work, and we apply that to two different purposes. One is to identify SOC change hotspots in the country, in the United States, where we would say, well, this particular land transition should probably be avoided in this area, or this land transition could actually increase soil carbon. And another application of our work is to develop soil organic carbon change emission factors that we apply in our life cycle analysis. That second piece is somewhat complicated, so I'm going to give a pretty high-level discussion of that today. But I think it's important to give a sense for how this modeling work is applied in this broader context of life cycle analysis that in the end can influence the eligibility of different biofuels under regulatory constructs like the RFS and the low carbon fuel standard in California. So as I mentioned, we use our modeling results to help us do sort of a hotspot analysis. I have a couple select examples here, again looking at corn and miscanthus as potential feedstocks and converting cropland, pasture, or forest to either of those feedstocks. So red means bad, so we have carbon emissions going on in that particular area if that land transition were to occur. Blue, on the other hand, means there's an opportunity for sequestration. So again, unsurprisingly, forest to corn transition is problematic. Our modeling suggests especially problematic in the upper Midwest or the Southeast. On the other hand, miscanthus, conversion of cropland pasture to miscanthus, because miscanthus is a deep-rooted crop, there's a lot of potential opportunity there for carbon sequestration. Now looking at these results, taking away the spatial aspect and putting a more quantitative aspect, and I'm seeing these are kind of small up on the big screen even, but we looked at, again, converting these 4 key land categories to corn agriculture, considering differences in tillage rates and stover removal rates and soil depth. So when you're looking at this figure, the blue bars are for there's no stover removal, green bars 30% stover removal as a just sort of rule of thumb removal rates. The lighter shaded bars are for shallow soils, dark colors for deeper soils. So a lot of information on this figure. But the key points I wanted to make here are that if you look at the median results, the bars in the middle of the boxes, for cropland and cropland pasture conversion to corn, you see that the median sequestration rate increases as tillage decreases. Makes sense, right? You till less, the carbon staying in the soil. So we can handle these types of agricultural management practices in our modeling and apply appropriate emission factors to our analysis. Grassland and forest, as can be expected from the empirical studies we looked at, we have soil carbon declines if we're converting grassland or forest to corn. On the other hand, if you're going to higher yielding cellulosic crops, we have actually carbon increases, again, in the cropland and cropland pasture conversion scenarios with higher sequestration rates than if you convert those land types to corn. The picture for grassland and forest conversions is a little more complicated. We looked at some short rotation woody crops, poplar and willow, and we found that converting grassland or forest, those short rotation woody crops, actually could cause a decline in soil organic carbon. On the other hand, converting those land types to switchgrass or miscanthus could result in either a sort of a neutral situation with switchgrass or potentially soil carbon increase with miscanthus. So again, this gives us a sense for general trends and helps us develop, built into each of these bars is a result for every county in the US. It gives us an emission factor to apply with some spatial specificity to our analysis. So in our analysis, we use these emission factors we've developed at a county level for these different transitions. This is somewhat of an advancement over what has been the case in many biofuel life cycle analyses where people may use IPCC emission factors, which is a great first pass estimate. There's some limited data there. There's about 9 or so reference carbon stocks that can be adjusted with these factors, and you sort of end up getting a more limited picture of what could be happening to soil carbon under these different land transitions. Some studies use rough assumptions. Some use emission factors based on a limited literature survey, and the emission factor pulled might represent a different area of the country might represent a different time horizon, so there can be some problems with mismatch when you use that approach. And these approaches in general don't take into account these key factors that can really drive SOC changes. Okay, so here's where I can get into some of our, I could spend another 20 minutes on this, but I'm going to try and cover it in about 3. The way that at Argonne that we incorporate those emission factors into our estimate of how much greenhouse gases we might expect to be emitted when land use change happens, we actually marry up results from an economic model called GTAP that tell us if you produce a large amount of biofuels over a number of years, where would you expect land use change to happen? What type of land is affected and how much of each type of land is affected? So we have those results incoming from an economic model. Then for domestic lands, we marry up those amounts and types and locations of land change with our domestic SOC emission factors. And for international, we have much less spatially explicit data. We use a kind of a standard data set. When we combine all these data, we end up with a grams CO2 per megajoule land use change greenhouse gas emission that gets added on to emissions from the main life cycle stages that people typically look at in life cycle analysis, like feedstock production. We have diesel fuel consumed by tractors, feedstock conversion, where you have natural gas consumed in the biorefinery. So all these material energy flows, carbon emissions, carbon sequestration, they come into play in biofuel life cycle analysis. And the key point that I want to make is that when we do this analysis, we try to take into account these very specific factors that influence soil organic carbon in the US. And on this slide, I wanted to give you a sense for how these land use change greenhouse gas emissions roll into our life cycle greenhouse gas emissions. You can see on the far right column, we have total life cycle greenhouse gas emissions for corn and miscanthus ethanol. I'm just giving you 2 examples of fuels that we've looked at. You can see immediately to the left of that column, the emissions without land use change. And then we include both domestic and international land use change to achieve that total on the right-hand column. The range in the domestic land use change greenhouse gas emissions comes from our examination of different agricultural practices. So for example, in the case of corn, till, no-till, those contribute to the range that you see there. We also have results for different soil depths. In parentheses are the results for a depth of 30 centimeters, and without parentheses, that's for the 100 centimeters. So corn, you see, has a positive domestic land use change greenhouse gas emissions, and that comes from essentially that the economic model predicts there'll be some forest converted, some grassland converted, and as we saw, those incur greenhouse gas emissions when those changes are made. On the other hand, the economic model predicts a lot of cropland pasture would be converted if miscanthus was going to be a major biofuel feedstock. And cropland pasture converted to miscanthus in general incurs carbon sequestration. So in the end, for miscanthus, we have sort of a credit, carbon credit associated with land use change because we are converting, we're basically using the soil now as a carbon bank to store more carbon. So this is sort of an interesting artifact of including land use change greenhouse gas emissions in biofuel life cycle analysis. Land use change greenhouse gas emissions can sort of tip the boat for biofuels, so the methodology used in calculating these emissions is very important. Again, there's these 2 pieces, the economic model, which is out of the scope of my talk today, and the soil carbon and carbon stock data that's used along with the economic model. And that's where we at Argonne have really tried to make advancements. So in conclusion, soil carbon, the influence on soil carbon of bioenergy feedstock production can be either way. It can be positive or negative. And to use soil carbon modeling to get a handle on that trend and driver, you really need to take into account these key factors that can influence modeling results. Soil carbon changes don't happen in a vacuum. They're influenced by the hydrologic cycle, which we take into account in our modeling through climate data, but they're also impacted by the nitrogen cycle, which is an area of research that we're working on currently. But in the end, really the objective is to take what's a fairly complicated system and understand what information can we pull from this modeling and from empirical studies to really help us understand where should we try and have biofuel feedstock grown to improve the ecosystem versus where is this not a good idea. And these are really what we need to, these factors are those that we need to take into account as we consider expanding feedstock production. And I have my acknowledgments, and I am done.
Questions? There's one way over there. Oh, let's get Randy right here.
Yeah, I have a question about banking the accounting for the carbon as organic material in the soil. When you are at a steady state, that will have a net no accumulation of carbon in the soil. You're simply talking about a short-term, be it 50 years, deficit in or enhancement in retention in the soil, something like that, a quick release from the change and then coming back to steady state?
Right, so there's definitely a temporal aspect, but in the end, the result that is needed is grams per megajoule fuel. So every biofuel LCA really needs to adopt a time horizon. We, in our analysis, the results you saw, that it is based on a 30-year time horizon. Because we run our own soil organic carbon modeling, we also do the soil organic carbon modeling over a 30-year time horizon, and so then we have the final and initial soil organic carbon, take the delta, and then that's the change that we apply to that situation. So if you wanted to look at over 100 years, the emission factor that we use is probably not the best thing to use.
Thank you so much for your presentation. I'm here. Well, my question is kind of the same. You said we should consider a period of time of 20 to 30 years for the soil carbon input or output. So in other words, do you expect to reach a steady state in soil within 20 or 30 years? And my another question is that, did you consider the variability in weather condition as well as management practices within the 30 years?
So yes, we expect soil organic carbon to return to equilibrium after 20 to 30 years based on the meta-analysis that we did. That shows the rate returning to zero after within 20 to 30 years, except for something like forest to corn. And then your second question was about
The
climate.
weather
So
variable.
what we do is we use historical climate data, and at present we don't take into account climate change in our work.
Thank you.
And in the last table, you had, for corn, for example, a range of like 63 to 66 CO2 per megajoule equivalent.
Yes.
A question I have is, what's your confidence in, that may give you, well, it's about a 5% variability you're projecting, but I'm skeptical that that's your confidence on that data. So, so that's one question. I guess the other question or comment I have, or actually a question is, you in the video you made the comment that we need to do a rational assessment and make decisions based on rationality, and I think your presentation does an excellent job of how we should go about that. But when you look at the discussions about GMO or global warming, many decisions are not necessarily, or policies are not necessarily made based on rational discourse. And so I just like you to comment on how firmly you believe in the comment that's recorded in the video.
Sure, okay, so first question was uncertainty. So yes, that results, so there, in our modeling we have two ways we can account for uncertainty, right? One is, the model at Argonne we use to do life cycle analysis is called GREET, and maybe you've heard of it or no. So within GREET we have a mechanism that we can use to do uncertainty analysis. The data that I showed you there didn't include an error bar, but we can, and we have done uncertainty analysis around that, and I'm trying to remember our error bars there, but I don't remember the range, but I can provide you with that. I think it's within, I want to say it's like within, definitely within plus or minus 10 grams per megajoule, probably less than that. the variability you saw there is purely from if you make different decisions in your soil carbon modeling, what does that range end up as? Rational decision making. So I am an engineer, and I would prefer that that when possible, that actually one of my motivations in the work that I do is to try and provide information that can inform policymaking. And I'm not so naive as to believe that emotion never comes into it. And certainly when you're talking about people's family farms and their livelihoods, emotions are unavoidable. But as a laboratory researcher, my objective is to provide the information that could be used in formulating policy if people care to examine it.
One last question, Tim.
So Jennifer, as you guys are working on this model, trying to apply it to different crops,
Yeah.
what are the biggest gaps or uncertainties in that modeling process that you would like to have filled now or in the next few years?
So definitely we need to be including nitrogen influence on soil carbon, and that's up for this year. Also, for cellulosic crops, there's just very little data. We can say we have the right direction, but whereas you can really do some model validation with corn, for example, right now it's really not possible to do that same level of validation with cellulosic crops. So we would always love to see more data for rational decision making. We'd love to see more data to help us validate and calibrate our models. And we always, provide a disclaimer as model. So that would be my wish list.
Let's give her a hand. Tom Richard.
Mic's working okay for everybody? No? Okay. So I'm going to start to play off some of the previous couple of talks and think about some of the big issues that people are worried about that many of you find out or find yourselves talking to. Is this better? Okay. And it has to do with two sort of different dimensions that I think are pretty interesting. One is food versus fuel. Of course, we've been talking about that since 2008 at least, and some people longer than that. And the other is a more recent one, at least on my radar, which is energy versus, or bioenergy versus forest. And I spent a lot of time in the last year looking at that, and there's actually sort of multiple interactions that I want to try to discuss. I'm going to, oh, yeah. So and the question is this a plus or a minus? Is it food versus fuel versus forest, or is it food and fuel and forest? And that's the topic I really want to think about in the next few minutes. So I want to start by talking a little bit about the pressures on food systems, some of the challenges associated with sustainable energy, and opportunities for food-fuel integration. I'm going to talk a little bit about some work that one of the students I'm working with is doing on dietary choice and land use, talk about energy opportunities on what we might call surplus land, and also some of the natural succession alternatives, forest versus grassland, and finally the advantages of integration. So I want to start out by talking about food, and actually it was quite interesting over the last spring. Many of you in the audience will have noticed that the Resource Magazine has been talking a lot about the 2050 challenges around food production, and that was mentioned earlier as well. This whole idea of going from 7 to 9 billion people, which actually, 9 billion is a big number, but it's only a 30% increase over where we are right now. When I was a kid, we had less than 3 billion, so that was more than a 100% increase over that time period. I'm a little bit more than 30 years old now, so I realize there's a time dimension there, but so far we've been kind of keeping up, okay? I wouldn't be so worried about that except for that other component, which is diet. So it's really not just population, but it's the multiplier of people times their consumption. That's true in many of our challenges today. And diets are increasingly land intensive, and they're increasingly using higher value or higher intensity calories, like a shift from grains to meat. And that means that the actual productivity of the land has to go up not just by 30%, but by 100% to a doubling by 2050. So that's pretty important. The other piece that, again, has gotten a lot more attention in the last couple of years is that we're wasting a lot of food. Now, people in this society have known that for a long time, right? And many of you have colleagues or work yourselves in terms of the supply chain issues with food storage and food losses along that. But it's a huge number, and it's a big opportunity as well as a challenge. I want to spend a minute or two on yield gaps and yield caps, and also climate change, which are also factors that are going to influence things over the next 30 years. So food waste. First of all, there's a little bit of noise in the numbers, but there's no question that we're wasting about 30% of our food here. And the most recent work, the black solid line there, did a good analysis of diet, actually suggests that we're getting close to 40% food waste. And most interestingly, that in the United States, that ratio or that fraction of food that gets wasted has actually been increasing. That has to do with new kinds of consumer behavior, the fact that we're eating out an awful lot more than we used to, so leftovers are kind of a thing of the past. But it also has to do with the convenience foods that we do bring into our home. And so there's a big, maybe a 10% increase that we've seen over a period of just over 30 years. In the rest of the world, it's also between 30 and 40%. And that's, in many cases of the developing world, challenges that we know have to do with actually energy in terms of refrigeration and the ability to dry and get food into a more storable fashion. So if we don't have sustainable energy systems, we don't really get to this food waste problem. There's also this concept called yield gaps, and this is some analysis by John Foley's group when he was at Minnesota. He's now out in California at the the California Academy of Sciences. This is a yield gap analysis for maize, but there's similar graphs that have been done for other crops. And what you see here, and I'm sorry the colors don't turn out too well, but the green are places where we're getting into the 60 to 80% of potential yield of what we know we can achieve with technology available today. But there are lots of yellow and red areas on this map where we're much lower than that. In many parts of the world, we're down in the sort of 25 to 35% range. And that's a huge opportunity, of course, for agricultural engineers and agronomists to really make some big differences in terms of the productivity. If we look at those productivity gains, and this is projected globally for maize, rice, wheat, and soybean over this period for the next 30 years, we see that there's opportunities to both maintain our current progress, but also potentially accelerate it if we get some of the tools that we know about into the game. However, even with these more accelerated estimates, we're looking at yield increases over this time period of between 40 and 60%, not the 100% that we would need to keep up with that expectation of dietary change multiplied by population. We also are in a situation where climate is going to affect food, and some estimates are that the impact might be 25% reductions in food productivity over those goals when we look at things at a global scale. We don't know that that's going to happen, but what we do know is that climate change is happening, that it's happening now, and that it has to do with our non-sustainable energy system. And so again, if we don't get these things coupled and working together, we're in trouble. This is some data for the Northern Hemisphere of the period when I was young, the 50s to the 70s, and shows what the mean distribution of summer temperatures were. And this is a typical Gaussian curve. And today, or actually in the last decade, we have still got a Gaussian curve, but it's shifted significantly. And what's particularly important is that upper end has gone where we used to have these extreme events that were the heat waves and the big storms that happened 1% of the time in any particular location. And now they're happening 10% of the time. And that kind of intensity is a huge challenge for agricultural productivity. On the other hand, we have energy demand increasing too. And this is estimates from the International Energy Agency of the different sectors of the economy and their expected energy uses globally. Here we're also looking at a 50 or 60% increase over what we're using today to meet demand. And one of the things that often happens when we talk about this food versus fuel conflict is that we think, well, we need food first, and then if there's some energy, will get away with it. As I've tried to indicate, there's some really important couplings there that we don't really get one without the other. And the other thing that I think we want to think about is when we think about development, that we have to think about energy as well as food as well. So this is some analysis of the primary energy consumption in different countries around the world and their success at achieving what the Human Development Index that the UN and other organizations have generated. And what you see, and this is not a big surprise, is that the companies that don't have much energy, that don't consume much energy, actually have not managed to achieve much human development. If we're going to move up that curve and at least get up to the area of a couple hundred gigajoules per person per year, which is what Germany and Israel have achieved today, that's going to take some effort, and it's going to take some more energy for everybody to achieve that than, in fact, those earlier projections indicate. To focus specifically on the transportation component, this is, again, analysis by the International Energy Agency, looking at what a transportation fuel portfolio needs to look like in order to limit global warming to 2 degrees over the next 30 or 50 years. And what you see is our current energy portfolio over on the left, largely a function of fossil fuels, some biomass energy, little slivers of other things as well. But over time, what you don't see in this figure is a big boost in solar or wind, because transportation fuels are kind of hard, as was mentioned earlier by Jonathan Mayle, to turn into the kind of intensive delivery system for many sectors of transportation. And by the way, this isn't just ground vehicles, but also shipping and air transportation as well. So it's all the transportation. And so the light blue bar that's growing as you look towards the future is the biofuels piece. And really, by 2075, needs to be at least 40% of our total fuel mix. And some of the other components here, by the way, that are expected by then, the electricity and the hydrogen, would also come from renewables and also may be largely bio-based, although solar and wind can contribute to those. So when I think about strategies for integrating food systems with sustainable fuel systems, biomass, bioenergy systems, I think there are a lot of places where we can actually get some win-wins to work together. And one of those is with strategic placement of perennials, again, getting back to Jennifer's and Rob's talks both, really. Sort of where do we have the opportunities to take advantage of more water or water and soil situations on the landscape, which actually may not be ideal for some of our other crops. So steep slopes where we already have concerns about erosion and soil quality, buffers along streams where we have concerns about water quality. These are really good places to get some of these perennials in the system. We know that and have known that for a long time. We also can look at the temporal opportunity for integration. How do we actually build rotations that include both perennials in the long term, but also take advantage of winter crops, which again was mentioned previously. There's also opportunities of co-product utilization, for example, livestock feed, and I'll share a little bit of information on that, and more efficient use of food, both through thinking about diet more efficiently, but also thinking about the waste that's generated from that food waste and how can we use that in energy systems. So, and these are just some slides of some of the ways that people are creatively doing some of that integration, buffers along streams, double cropping, and winter cropping as alternatives. And this is some work that we did, some analysis a couple of years ago, looking at winter rye, which is one of my most favorite winter cover crops, but also a winter energy crop. And by the way, when Jonathan talked about Mayle talked about the updates to the billion-ton study, we're not sure yet, but we're trying to get this cover crop option in there. Our estimates are that just on the corn-soybean acreage, slipping a winter cover crop, winter rye, into the fallow period in the wintertime without changing the corn planting or harvest dates, and in fact giving a little bit of buffer to get those operations done, we could produce 150 billion tons from that crop alone. And it's land that's already in agricultural production. In fact, that crop would improve the soil quality in many of those fields and also enable things like corn stover removal at higher rates without having big carbon deficits. Co-products. We talk about land use change and sort of the challenges associated with that for some of the bioenergy crops. But we also can think about some of these synergistic benefits there. So this is analysis of what the net land use in terms of hectares for billions of tons of, I'm not sure what, biomass energy equivalent, that's what that is. But it doesn't really matter. The red bars are are what's typically done in the first round calculations, but the green bars are what happens when you actually take the food value of the byproducts of the energy system and put that back into the food system. And you see the difference between those red and green bars is quite substantial, particularly for things like maize or wheat, where we have a distillers dry grains and solubles type product that can go directly back into to livestock feed. So that's another component that I think we need to think about. All right, I want to take just a few minutes to talk about diet specifically and share some analysis that we're doing right now to look at two different possibilities. One is the USDA dietary guidelines for a healthy population. And by the way, I was just reading that we're finally starting to turn the ball a little bit turn the corner a little bit on the obesity epidemic in the United States. And it looks like part of that is people are actually thinking more consciously about their diet, particularly younger people, which is wonderful. But we've had this transition for actually more than a generation of shifting from beef to poultry, which has got a lot of factors associated with it, one of which is quite simply cost. There's also been sort of the red versus white meat discussions with respect to health. And we did our analysis imagining that particular protein shift would continue for another 17% drop, which is what we've seen before. This is some analysis which really was an eye-opener for me. So this is on the left, it's the caloric intake, or production rather, that goes into the U.S. diet. And the big green piece is the non-animal food. So we get most of our calories from wheat and maize, and when it's directly consumed from us, and rice. And we also export a lot of those calories as well. And then the thin slivers of color there on the upper left and at the top are the various components of meat, which are not a very high caloric part of our diet today in the U.S. But if you look at the right bar, what you see is those meat components are over 3/4 of the land requirements for food production in the U.S. So we go from something on the order of 10 or 15% of our food caloric intake to something over 3/4 of our land use. And the flip side of that is that challenge that we were talking about earlier when we talk about feeding a population that wants to go in the opposite direction, right? That wants to get a lot more meat calories in their diet. So what we did was we analyzed the alternative diets, dropping beef production by another 17% and increasing poultry to meet it, and also shifting to the dietary guidelines of the U.S. And this is a very busy slide, but I'll just point out there are 3 numbers on here that I want you to pay attention to. They're all on the far right, and they're underneath the pie charts. And those are the amount, the required acres and millions of hectares required to meet those diets. The top is our status quo, 415 million hectares, roughly the agricultural production in the U.S. right now. The second one is the dietary guidelines. If we adopted those as a nation, we would only need 369 million hectares. And the third is the protein shift, 355 million hectares. Again, these are things that was a voluntary process that we've already observed. So if we look at the difference between those land areas and do the analysis of what we might grow in bioenergy crops, we actually think we can produce on that land that's currently being used for dietary production between 30 and potentially in some scenarios up to 100% of our gasoline requirements in the U.S. So that's a pretty interesting piece. And this is a lot of different scenarios looking at both energy crops right now as we grow them today, also what we expect yields to be in 20 or 30 years, but also technology develops in terms of the efficiency of conversion. All right, so that's not maybe a big surprise to the people in this room that if we take 15% of our land out of agriculture production, we can actually grow a lot of energy on that land. What was interesting to me and what kind of a surprise was when we looked at the land use shifts, and most of the land that we were shifting is pasture land because that's where a lot of our beef is grown, that when we compared what alternatives might be done with that land, and we looked at kind of an opportunity cost if we're going to shift land out of agricultural food production and into energy production, what would happen if we didn't shift it into energy production? what would happen if it was abandoned and turned into grassland in most of the central part of the U.S. or forest in the east. And those are the upper two sets of bars. The upper one is the forest, and then the second pair are the grassland. And what we see is, and then the third is the spared land total, so the combination of grassland and forest land that would happen based on ecoregions of the U.S. What we see is between 1 and 10 megagrams of CO2 equivalents per hectare per year. And the forest really is awesome, generally producing, and this is mostly eastern forest that would be converted, 9 to 10 megagrams of CO2 per hectare per year for a long period of time. This is an average of the first 30 years, okay? And if we look at the biomass carbon equivalent off those same acres, and these are the bottom 4 graphs, or two sets, both the current at the bottom 2 and future technologies, we get somewhere between 8 and maybe 12 or 13 megagrams of CO2 equivalents per hectare per year. And that's including both the offset value for the fossil fuel that would no longer be used, but also the soil carbon and other things that would be benefits. And so what's interesting is these forests are actually really productive, and that's just without any harvest, just accumulating biomass relative to some of these energy systems. So that was a bit of a surprise to me, and I've looked into it a little bit more, and there's actually an inflection point. So this is the time scale. Those were 30-year averages that I mentioned, and I'm sorry these lines probably can't be seen too much by you, but what you see is over around year 15, there's sort of some, this is the first 20 years, some crossover lines where biofuels relative to forests and combined with grassland start to show dividends. But in the first few years, because of that forest productivity, it's pretty dramatic. And when we average the entire eastern forest, it might take up to 45 years before we actually beat out the forest. Now, most of you know that the forest eventually would reach some kind of equilibrium steady state, not just the soil part of it, but the above ground biomass as well. And so if we decide to let the forest take care of our carbon mitigation for the next 45 years and don't start building biomass energy systems, we actually are going to top out that forest opportunity. The beauty of the biomass energy systems is they keep giving these carbon benefits year after year after year. So eventually they always win out. But the question is, how do we start? And also, how do we talk to ecologists and environmentalists that do recognize correctly that there might be some trade-offs in the near term? The other piece, and I'm about to close here, is that when we look at the forest sector, and this is some really nice data, so I'm sharing it, but I think there are similar data sets that can be generated for agricultural sectors. What we see is that the combination of ecosystem storage, materials use, which is what we use our forests for mostly right now, and energy production actually are incredibly productive. And that's, I think, where we need to go. So in this graph, and this is for the California forest, Bill Stewart at Berkeley put this together. If we look at there's a solid line here I think you can all see that starts out over on the left and kind of works up, and it takes actually 160 years in that forest to reach more or less steady state, so over a planting after a clear cut. In this case, there's cycles of activity every 40 or 80 years, and each one of those activities of harvesting will generate energy and materials, and those energy and materials have a life cycle, and over time they emit carbon as well. So I don't want to go through it in all the detail, but the important thing is that it takes roughly 60 or 80 years to make the shift from the ecosystem doing really well relative to a managed system to the situation where it's actually producing more if we do manage it. Of course, our forests in the U.S. have been managed for more than 100 years, so we're already at the point where we're reaping those long-term benefits. But if we take the energy piece out of the equation, the benefits are only about half what they would be with the materials. The materials piece is really important, and again, something I hadn't really understood as well, but those woody materials are substituting for concrete and steel, and they're very energy intensive. And so if we don't use them for that purpose, there's carbon benefits left on the table. And in fact, per ton of wood, those carbon benefits for materials in many uses actually beat out what we can get with energy. So that's pretty substantial. But the synergies are important, and that's my fundamental message. I'd like to have us doing this kind of analysis in agricultural systems and looking what the food, energy, energy and ecosystem benefits are together in those systems as well. All right, so some conclusions. First of all, there are opportunities for synergies as well as conflicts when we look at food, forest, energy. This is one that I think is worth some discussion. This ethical hierarchy where food's first and then energy, I think we ought to challenge that occasionally, because I don't think we get the food benefits that we want globally for society without a more sustainable energy system. And for many people in many parts of the world, the way to get from up the Human Development Index from where they are right now, if they're not starving, and many people are, but you get beyond the 1 or 2 billion people that really have serious food security issues, there's another 3 to going 5 billion people that really need energy badly, and that's going to make a big difference in their lives. So there's going to be competition for prime agricultural land. I don't think there's any question about that. And I also don't think there are any questions that there are synergies to be had with integrated systems. As engineers, I think we have to think about what are the time scales of some of this analysis and what are the system boundaries. Again, you've seen that from both of the previous talks, that these are really important when we think about what's happening where and how these things are moving and how long it takes to reach equilibrium and how we build those things into our calculations. And finally, that I think in many cases, because of the heterogeneity we have in soils and soil types and climates and in economic context and in skills, that there will be different solutions for different locations. And I'm not sure that our markets or our policies are going to send the right signals to get to the best solutions in different places. So, thank you, and I guess we might have a couple questions.
Yeah, questions?
San Fernando from Texas A&M. Tom, you did a great job in explaining the nexus of food and energy. And the question that I actually basically have is on the intersection of the three. What I mean by the three is the water, food, and energy. So I'm an experimentalist, and I can clearly see the nexus between like water and food, or food and energy, or energy and water. But when it comes to the intersection of the three, so as an experimentalist, I'm kind of finding it difficult to comprehend what sort of research is necessary, or what are the questions that we have to ask. So do you have any comments or direction for those of us who are primarily dealing with the experimental part of it rather than modeling?
Thanks, Sandun. So I'm actually going to, okay. So thank you, Sandun. And I'm going to actually also invite my co-panelists to offer comments on this question too, and maybe ask that if other people have questions which the other folks can answer also, we can hold those for the general panel. So if other questions are about my specific talk, that's fine. I can take a couple of them. But Sandun's question was, as experimentalists, when we think about this interest in the intersections between food and energy, food and water, water and energy, and all three together, which I think everybody in this room knows is an increasing interest of the National Science Foundation, as well as USDA and DOE and others as well. What should we focus on? And there are lots of bilateral connections that I think are pretty apparent, so I'm not as worried about that, but it's the trilateral ones that are harder. And what I've tried to illustrate in several examples that I gave is that, in fact, that's where the interesting interactions are. There's some very interesting interactions. And I think it will be location-specific. So one of the great things about having researchers working in this area all across the nation is that we can think about the agricultural systems in our region, and maybe I should say more generally, the landscapes in our region, and how they might be managed so that they can produce all of these products and ecosystem services that we need in an effective way. And I think coupling things and thinking about both space and time as we manage these systems and where can we get the benefits is going to be a large part of the solution.
You want to address?
Did you want to say anything to that?
I have some work at Argonne looking at, our area. So a field, if those of you who saw the video, saw Christina Negri and Eric Rund speak about a field site that they have looking at ways to integrate bioenergy feedstock production with conventional agriculture. And one aspect of that work is to really understand the ecosystem services that the biomass can provide and reducing runoff and things like that, that then improve water quality, and it all comes back around. So I think we're starting to see some significant research projects in this area that are going to help us understand how all these things come together.
I mean, my response is really simple, right? As a modeler and an analyst, we like data, and we need data. And so what do I mean by that? If you're running an experiment, and I understand the problems with this because I am an experimentalist as well, but if you're running an experiment in the field and you're interested in nitrogen response, well, if you happen to also measure the other domains, right? I mean, so think about what were the impacts on water, and are there some data that I can collect here without great cost? And I know that's the problem. But whenever we're designing a piece of equipment or anything, think about, are there other pieces of data that would bring in other domains that would allow somebody to then do analysis?
And on that, I'll just offer a little bit of an anecdote. So, most of us in the room know that people have been doing work on sort of what is the energy footprint of these bioenergy crops, because that's important in doing the life cycle analysis. So we did a study of that for production systems for 15 crops in the United States, and only 4 of them were energy crops. Most of them were food crops, and we sent it out to a journal, and the first set of reviews that came back were all about how this was just another bioenergy crop study. They did not notice that we were talking about soybeans, which are a energy crop, but also, rapeseed, but also wheat and cotton. And is cotton an energy crop? Anyway, so my point is that doing this analysis is actually really important to do for all of the components of the system, not just the energy crops, and understanding how we can make more efficient systems for all of our production.
Let's give Tom a hand.
Yeah.
What I'd like to do is cue up those 2 slides that I mentioned. Neglected to start with these, but why not use these as the transition from what we had heard about to additional questions and answers that we need to consider. The environmental systems, the challenges there, the human systems, again, the challenges. And then in terms of analytical and policy issues, what we have in terms of system boundaries, timescales, treatment of uncertainty and risk. And I wanted to leave that last question up there. Thanks, Tom, for preparing that. What are our responsibilities? I can't think of a better society, technical society, to address all of these issues. My problem is I tend to think too locally. When Nana says I'm going to go see the grandkids, we need to spoil them, I think, okay, what can I do to improve their quality of life? But actually, what I need to do is consider the grandkids overseas, developing countries. How can we, as a technical society, improve their quality of life, whether it be food, water, energy? So with that, we open up for questions for all of the panelists. Do we have some? Shahab, right in front of you.
Well, Ray, I agree with you that we really have to work on this thing, and we'll do that. But I think one of the great function that we might have is how we inform the society. It's wonderful to do research and experiment and so forth. How do we inform? For example, Tom's comment regarding forest, if you don't really use it for energy, it's worse for the environment. How that message, how you translate and document that for public to understand what we're saying. Or Jennifer talked about reduction in soil carbon if you go to a to a short rotation with the crop. I think that's what I understood from your statement. So how can we translate into this thing some of them are not really in unison in terms of, the results of the scientific. How can we inform these things to the society so we don't get these recent problems with forests are being burned to supply power to Europe and, things like that?
So I'm going to guess that we're supposed to all use the mics. Is that right? No, just me. Yours are working, apparently. Okay, so I'll start. And so, I think that there's really a whole scale of interactions where we can help to educate people about some of these ways of thinking about systems that I think are important. And it starts with your family and friends and sort of, when somebody challenges you about something that you think they can think about differently, to share that. There's lots of dinner table conversations or coffee breaks or whatever that I think we all participate in. But I think many of us in the room work in education, and there's a tremendous opportunity for that. Although I have to say that some of these issues are much better dealt with at very much larger populations before higher education, in the elementary schools and the high schools, and so finding ways to reach out to those audiences, again as individuals, but also as groups, and preparing material that's appropriate. And I think a lot of this has to do with really general kinds of problems. One of the things I've loved about bioenergy is that it's a great platform for doing analysis of all kinds of things that are actually interesting to young people and illustrate general challenges that we have to face as a society. System boundaries. Well, as engineers, we've been putting system boundaries since we were freshmen in college. But in fact, other people, everybody should be doing that when they think about problems much earlier than that, and it's really useful in lots of different areas of society. And so anyway, that's I think all of these things would fit into that category.
As Jonathan mentioned, it's for part of the broader DOE effort to increase communications, and he asked, why is this important? And I couldn't agree with him more that it's important. It's difficult to find the time to do that when you're engaged in all this research and everything, but I think it's important to get the message out. And at Argonne, we continue to work with our other national lab partners and with BITO to try and get the message out in a way that's digestible for young people, but also for adults who have a lot of messages being thrown at them, from dietary information to how we should be changing our energy supply.
I don't know that we all need to answer, but I will anyway. Tom said something about age. I definitely grew up in the era of you got your information from a few reputable sources that you really sort of believed in, right? You watched the evening news with Tom Brokaw or whomever. And it feels to me, again, this is a reflection of my age, I think, that we live in an era where there's lots of ways to communicate, and really too many ways, right? It's like everybody's in the room trying to shout louder than the other guy, and all the social media are wonderful. And those of us who are educators, I think, need to work with our students to help them figure out how to be smart consumers, right? How to figure out what's a reputable source and sort of who to listen to, because we're not going to shout louder than the other people, right? It's not like we really need to do a lot more putting out of information. And to some extent, I don't think we can educate people in that public arena. We need to help make people be better consumers of information so they know to pay attention to Shahab when he tells them the truth.
So I'm hearing communication definitely is key. I would suggest that we need to communicate a single, uniform, standard message throughout. Too often we get hung up in our own little areas, and we want to fight for that particular area, and not necessarily consider what's happening in a global sense at the same time. Other questions?
My question is, there are a lot of talk about the LCA in this session. So as an LCA practitioner, how we can standardize doing the LCA? Of course, there are some methods in ISO, but still we can see that the LCAs are publishing, the LCA studies are being published, but there are a lot of varieties in them, and it's not very standardized. and how we can make it, as you know, data inventory is really, really important in doing an LCA. But still, I think in Europe, they have a very strong database, but in US, we suffer lacking data, a good database, a valid database that we can use as an LCA practitioner, and we're sure that the results are kind of valid, because these results can be a base for making policy. So what's the solution for making a big and good and a strong database that LCAs in US also become much more valid? Thank you.
Okay, so there's somewhat of a challenge regarding data. So for something like corn production, we have lots of data. The USDA is amazing. The data is there for something like corn, something like soy. When you talk about something like switchgrass, miscanthus, short rotation of woody crops, the data, it's an emerging system. There's limited data, and that's just how it's going to be for some time. And so, at Argonne, we have this model we build called GREET. We take the best available data we can find, and we put it in our model. Those data are publicly available. USDA has a database that's publicly available. I would suggest that, yes, Europe has a database. I speak with people who do LCA in Europe, and it may not be as wonderful as we might expect, because data change. There's a temporal aspect as well, and that's, at Argonne, we continually revisit data even for corn, even though, as Jonathan said, DOE doesn't really fund ethanol research anymore, but nonetheless, we need to keep track of what's happening with corn, because corn ethanol is the big biofuel in the US. We have to have up-to-date results for that biofuel in order to talk, about how that compares to gasoline or other fuels, and how newer fuels might compare to corn ethanol. That database, or that baseline, needs to be continually maintained. As far as standardizing an LCA methodology, you are correct. There are things like ISO standards. For bioproducts, there are any number of certification routes, or for biofuels, there are certification routes through ISCC and other venues. To me, I guess I'm somewhat skeptical that there will be someone that will say, this is how we're going to do it, and everyone's going to follow suit. I doubt that's going to happen. I think what's important is transparency. So when someone does an LCA, they say, this is the data that I use, this is where it came from. If I have co-products, I handle them this way. Here are the other assumptions I made that are relevant. And if there's a philosophical choice involved in the analysis, perhaps both sides of that philosophical choice should be presented. So one example I was talking about yesterday with someone was how water consumption is allocated to corn stover versus corn grain. Some people would say, well, corn stover is, it's a byproduct, waste product. You don't grow that field of corn for the stover, you grow it for the corn grain. So corn grain gets burdened with all that water. Some people say, yeah, but you're getting a useful product from that corn stover, so maybe you should allocate somehow based on mass or based on something else. That corn stover should bear some of that water burden. In some ways, that's a philosophical choice. So perhaps life cycle analyses that are making some sort of philosophical choice like that, you need to present both sides of the story. And unfortunately, it is, it can be kind of complicated. And I realize, getting back to this public education issue, people have somewhat of a low tolerance for complications, but I just, in some ways, I don't see any way around that through standardization at this time.
Thank you.
Another question?
Hi, thank you very much for the talk. I guess I had a question in regards, going back a little bit to communication. It seems that a big part of the problem is that lack of communication between the more research side, the more technical side, and everything else. So from your experience, what are different opportunities or different outlets that we can start looking for potentially interdisciplinary work in which we can work alongside with social science people that know better ways or have a better handle on how to communicate these very important issues and tackle problems such as emotions or problems such as consumer decisions at the end of the day?
So I can start, because this is actually a favorite topic of mine. communicate with the public effectively. I'm not going to say I'm very good at it, but I'm trying to learn. And we actually, at Penn State, the organization that I manage there, we're spending the month of October this year having a science communication month to try to teach lots of faculty how to actually do a better job of that. And there are some people that have some pretty good skill sets in this. Some of you may know the name Naomi Oreskes. She's been doing a lot of work on climate and trying to understand how to communicate that more effectively, but also other controversial topics. And there's a lot to learn about how to communicate with different audiences. There's a whole field called cultural cognition where you sort of have to think about tuning your message to the people that you're talking to and understanding their value system, and making sure that you're not saying things in conflict with that will turn them off and keep them from paying attention to the technical information you have. There's a good book I can recommend by a woman named Nancy Barron, who runs an organization called Compass, and her book is called Escape from the Ivory Tower. So for those of you who work for universities, there's a subtitle there. I've forgotten what it is. But anyway, there's a number of different things, tools that we can take advantage of to become more effective communicators, whether it's with a group of high school students coming to visit a campus, or Rotary Club, or a church group, or somebody on a testimony to a Senate or state committee.
Yeah, I'll echo what Tom said. Actually, at Argonne, we had a training delivered by the Alan Alda Center for Science Communication that was very interesting. And it's a great group working with universities and many other people. So I think that there's definitely a recognition that those of us in the technical sphere need to improve our communication skills for a more general audience, and I think it's fun.
And I think part of the question was sort of, how do we find people to partner with? Was that? I'm not
Social
sure.
scientists.
No, I guess it was more along the lines of maybe thinking outside the box, or maybe not, maybe thinking in terms of how can we meet engineer and social and maybe doing research together alongside. Because I think that sometimes, at least from my experience, there seems to be two separate fields, and we're missing communication with each other.
Yeah. So I think that, some agencies make us do this, right? So the National Science Foundation, at least in grants of a certain size, they talk about broader impacts, but they absolutely want built in a component that has to do with communication, and furthermore, they have certain solicitations that are all about a joining of the, if you will, physical, natural sciences and social sciences. And so I've had some of that money, and I would say, sort of echoing, I think, what was said, is that go out there, look across campus. There are people out there who would be very happy to work with you and who know a lot about communication, but even know, so I'll give an example, right? As an engineer, I like efficiency. And I don't necessarily always want to go talk to somebody who's going to say, well, let's have a very long conversation about this, and we'll bring in 75 people, and it's like, oh, okay. But I worked with Will Fote at Oklahoma State, and Will, one of the things he does is he's got a sort of a framework, and it basically includes, well, there are issues that are either not salient enough, not important enough to people that they don't want you to waste their time talking about it, or they trust the technical experts, and so they will defer, right? And so there's a framework of how to communicate to different groups about different issues, which I found incredibly useful. So there are people out there who can help us, and sometimes even in ways that engineers appreciate, that help us say, no, we don't have to have a long conversation about this one. So reach out.
I think Jim had a question.
Yeah, this last conversation was great because it kind of sets it up. The communication and a lot of the influence that we're focused on today is influences culture, beliefs, and values, and how people perceive bioenergy as good or not good, or the trade-offs as good or not good. In the other community that Jonathan got at quite a bit, and with Beto Office, I've had a lot of conversations the last couple of years how do we monetize the risks, the uncertainties, the benefits, the non-market values, if you wish. But we heard about exporting virtual water outside of the United States. So what's that worth to corn growers, farmers, citizens in Iowa? The soil carbon balance, whether that's positive or negative, and ultimately, how do we translate that into tax policy or values or transactional values? How do we value water quality and the like? But as we do that, the investment decisions in bioenergy, the policy decisions in bioenergy, eventually come down to tax policy or economic investment or transaction costs. And as engineers, we need to do a better job and learn, much as we're learning today how to communicate beliefs and value assessments to the public, to the investment community, to the policy, office of management, and budget level people.
I'm not sure there was a question, but
The question was, what's your discussions going on about how you move from the beliefs and value communication to monetization, tax policy kinds of discussion?
Yeah, well, so, I mean, I've played in that world a little bit, right? So, I mean, there are lots of economic tools that require a lot of effort to try to monetize non-market things. And that's a wonderful jobs program for a lot of environmental economics professors. And not to say that isn't valuable, right? But we can't really do that for everything. And so I think creating policies that essentially create markets, right? That let people express their value for things. And I know that's not always popular, but creating, letting people basically buy the things they value. And so when you were talking about water, right? I mean, in some ways, okay, great, there's virtual water and we're trading it. And so the market ought to be able to give us good signals. The problem is, of course, is that water isn't traded, right? And it's not valued. There is not a value, a price put on it that represents actual demand, right? So farmers don't bid for water. In a lot of places in the US, there are even policies that encourage them to use more water and to use it poorly, right? So places that have appropriative water rights, people want to use all the water they can possibly get, or next year they may not be able to get as much. So there's all kinds of things there that are both legal and legislative. The federal government actually just overrode some of California's water agreements to basically circumvent what might have looked like a market enterprise. But I guess that's a long way of saying I think we can create ways to let those things monetize themselves, and when we can, we should. Beyond that, well, there are certainly methods that economists can bring to bear that will help us do that to some degree.
So I have a couple of examples, and one is there's actually global markets for carbon now, but one of the things that came through so far is that a lot of those markets for terrestrial living ecosystem carbon require that you not actually harvest any of that for 100 years, okay, or longer. And so that, I think the evidence I shared, at least for forest, I think for agricultural systems, is that's really not the smartest thing to do in many systems in terms of overall carbon reductions. But that's the market that we structured so far. And so I think working with the people that actually are active in those markets to open up their eyes and help them think about alternatives is a good idea. And there are some organizations right now that are actually making a lot of money selling, I guess, the equivalent of development rights, harvesting rights to forest land in the United States for carbon benefits. And some of those organizations actually realize that what they're doing is not the best thing. So there's, I think, an audience, at least in the forest sector, that's willing to rethink the way those carbon markets are set up and create opportunities to monetize the carbon benefits of different kinds of management. I happen to live in the Chesapeake Bay watershed, and there is a market for nitrogen in the watershed that's existed for about 6 or 8 years now. actually a pretty lousy market, but it does exist. The wastewater treatment plants in the region are allowed to buy nitrogen credits from farmers who change their production practices in ways which offset the nitrogen emissions from those wastewater treatment plants. And there is some participation. The prices have been really kind of shockingly low, and the demand has been relatively weak. And so I think there's a start there, but it needs to be strengthened. And actually one of the things that we're working with is trying to figure out if we can get bioenergy crops to play in that market effectively in that region as well, through the buffer strip ideas and other landscape change strategies that we think would make a lot of sense. One of the challenges is that for the regulatory agencies, and I would say the consumer markets as well, they want some concrete evidence that things are actually going to stay the same for a long time. Because when they're thinking about these impacts, they don't want to pay you money now and then you're going to switch things out in a couple of years. So working out those contractual relationships for the long term that actually will guarantee the benefits that people might be willing to pay for is another part of the equation.
And I'll just say that the Chicago Metropolitan Water District has a similar, they're putting together a similar program to monetize nitrogen as well. That's in the early stages.
We should look at those because another $20 a ton for nitrogen benefits, which is what our first cut analysis suggests should be achievable in our region. That's a big chunk of that $80 a ton that was mentioned earlier today.
Well, and in fact, you mentioned risk, and Tom touched upon it, right? So the Chicago carbon market fell apart because primarily the purchasers didn't have confidence that they were getting their value, right? It wasn't just the length, will these practices stay in place, but the scientific uncertainty around, is there even carbon that's going into the ground? And of course, will it stay there? And as people have generated nitrogen markets, and California has a nascent one as well. I seem to know a lot about California. There's really that question, right? I mean, for a market to work, for the market to clear, there has to be confidence in between the seller and the buyer, right? And that's someplace where we have something to say, right? So if the data aren't presented like, well, I've got a spot estimate that I'm saving 20 pounds of nitrogen, if you can put with 95% confidence you're getting 15 pounds of nitrogen, that changes the market significantly, right? So we can run probabilistic analyses and we can put probabilities on these things, and that will make markets work much better.
Cycling back to the communication aspects, sometimes we think that the public is a homogeneous group, but it in fact is very, very diverse. And whenever you develop strategies, and this is not a question, it's just really a comment, is that you really have to define multiple audiences and structure communications for those audiences. And one example is in Hawaii, we have a big native culture. And what you can communicate with people like engineers or policymakers, the conversation is completely different when you're talking with native populations. And if you want a communication program to address issues of concern to them, you have to structure the communications. And so, one size is not going to fit all. And so it's a very interesting and complex process to develop a strategy in communications.
Other questions?
I'll just follow on that since no one immediately asked a question, which is, sometimes it works the other way around. The Native American tribes, the Menominee Nation in Wisconsin, has a history of wild rice harvesting. And so they're very interested in water quality in terms of, the things that they've traditionally done, traditional practices. But it's amazing how, or it was surprising to me, how them talking about that actually communicates to sort of the larger, whatever, we invader population. Because people can actually understand that. And it's actually a very eloquent statement of why water quality is important, and it's a, sort of a physical manifestation of, we scientists talk about all these various measures and they don't mean anything, right? I mean, I don't know, eutrophication potential, whatever the heck that is, but, when you talk about something quite tangible that affects people's lives and their culture, it makes a very effective carrier of that story.
I think we'll close at that. I do appreciate the panel, Tom, for putting together the panel. Let's give them a hand.